So coming to question number 10 now, it says, refer to the figure, the time varying magnetic field is present in a circular region of radius r in the space. A charged particle q is placed at a point A at a distance d from the center of the circular region. Calculate the work done by the induced magnetic field in taking the charged particle from A to infinity along the given horizontal line. Basically इस क्वेश्चन में हम लोगों को एक टाइम वेरिंग मैग्नेटिक फील्ड दी हुई है एक सर्कुलर रीजन ऑफ रेडियस आर में, और हमें दिया है कि एक चार्ज पार्टिकल Q है जिसको हमने एक पॉइंट A पे एट अ डिस्टेंस D फ्रॉम द सेंटर पे रख दिया है, और हमें जो मैग्नेटिक फील्ड है द इंड्यूस्ड मैग्नेटिक फील्ड, वी हैव टू कैलकुलेट द वर्क डन बाय इट to take the charged particle from A to infinity along the given horizontal line in the question. और हम लोगों को मैग्नेटिक फील्ड दी हुई है B नॉट T के फॉर्म में, that is coming out of the plane. So let's see how to look at this question. वैसे it's a काफी lengthy question, so generally काफी लोग ऐसे ही छोड़ देंगे, but I would say not to leave the question and just try with the concepts you have. Let's see how to solve this question.
See, we are given a time varying magnetic field, right? So because of a time varying magnetic field, we are going to get an induced electric field, and this induced electric field will be concentric circles. I have explained you a bit earlier. See, the magnetic field is only present in the circular region of radius r. So for a distance r from the center of the region, ER would be B naught x by 2.
That's right.
For r less than r. But for ER would be B naught into r square by 2x for a distance for x, right? Okay. X greater than r.
Exactly.
So I have even plotted a graph before that ER would be increasing till this, and after this it is starting on decreasing. So here at this point would be B naught into r square by 2x, and it will be in this direction. It will form a concentric circle, right? ER. It would be in this direction. See, if the charged particle is going to move along this direction, what happens is the ER is going to change with respect to this distance x. If this moves by distance x, let me think. Suppose it moves by distance x, the radius it gives at the center of the circle would be different, and the radius would be under root of x square plus d square.
That's right. Just by simple Pythagoras theorem.
The ER at this point would be in this direction, right?
Right.
And this magnitude of this ER would be EX, okay? Would be B naught r square by 2 under root of x square plus d square.
Exactly.
And this and the component of force along this direction is going to move the body, is going to do work on the body when this body is moving from A to infinity along the given horizontal line. So the component of force, the component of electric field along this line would be, if we consider this angle as theta, the electric component of force along this line would be E naught Ex into cos theta.
Right.
Only this component of force is going to do the work, and the force acting would be Q into Ex cos theta along this direction.
Exactly. So basically we see that visualization is again very important here.
So the work done by the particle on taking this from 0 to infinity would be nothing but Q into charge of the particle. This is nothing but the work done by the induced electric field.
Right.
Ex into cos theta dx. Fdx, work is nothing but the force into displacement.
True.
From 0 to infinity.
We need to keep in mind, the easy formulas that we do put in such big and difficult questions. I mean, the basic formulas we should never forget.
And this one, the cos theta is also varying. We have to remember, because see, if a particle is over here, the theta is increasing gradually. So for each small displacement dx, the small work done parts will be different. So what is going to happen is, the cos theta value would be at any time. Let me calculate the value of cos theta. If this is theta, even this would be theta, right?
Right.
And cos theta would be d by under root of x square plus d square.
True.
So I am substituting this value over here, and I am even substituting the value of Ex over here. That is nothing but 0 to infinity q into b naught r square by 2. On substituting the cos theta value, it will become x square plus d square
That's right.
dx into dx. I am taking the constants outside the integral. It would be q b naught r square.
Exactly. We just have to do simple
by
mathematical integration now.
0 to infinity dx by d square plus r square. On integrating this, we will get this value. And the most important thing to note here is, this is independent of d. So wherever the particle is placed, the work done by taking the particle from that point to infinity along the horizontal line would be the same.
That's right.
This is the most important point to remember.
So basically, this was question number 10, and we saw that in this question how the question seemed to be a quite lengthy one, and it wasn't, the solution was although not that much. What was important was the visualization of the question, to see what actually is happening in the question, and after that some simple mathematical integration. So basically this was question number 10. So heading on to question number 11, it says a square loop of side L, mass m and resistance R falls vertically into magnetic field directed perpendicular to the plane of coil from height h, so that the loop falls and attains terminal velocity during entering. Right.
See, here what happens is, when loop falls to a height h in a non-magnetic region, it is going to attain a velocity of v equal to under root 2gh. We all know this, right?
That's right.
By the time it reaches this point, this particular point, by the time it reaches over here, what will happen is, because of this velocity, there will be is going to have a velocity v, which is equal to root 2gh over here, and because of this velocity there will be, and because of the magnetic field B in this region, as the loop is going to enter by, you know, I have done this problem earlier. You should have remembered that when a block is going into the region having a magnetic field B, the induced EMF would be BLV.
That's right.
The EMF induced in the ring would be BLV. And given that the resistance is R, so the current induced would be BLV by R. So because of this current, as it is going to enter into the magnetic field, magnetic force is going to act on this bottom part of the wire.
That's right.
And this magnetic force would be equal to BIL. We should all have dealt with this earlier. So this magnetic force acting on this would be B into the I is given by BLV by R. On substituting the values, we get B square L square V by R. So this is the magnetic force which is going to act on the wire. So on the bottom part of the wire, you see mg is the force acting on it downwards, and this Fm is the force acting on it in upward direction.
That's right, exactly.
We are going to write differential equation mg minus BIL. BIL, that's nothing but B square L square by V by R equal to mdV by dt.
just equating this being the force equation.
Now they have given that it should fall with a constant velocity. If it should fall with a constant velocity, the acceleration must be 0.
That's right. So dv by dt will
Must
tend
be
to
0.
0. That's right.
If the dv by dt must be 0, then what should happen is the mg must be equal to b square L square v by r when the loop is going to enter the magnetic field.
That's right.
When the loop is going to enter the magnetic field, the v would be root 2gh. So we are going to find the velocity for which, we are going to find the height for which the loop will just enter the magnetic field without any change in velocity.
That's right.
So if there should not be any change in velocity, what should happen is, this must be the condition. So we, on solving this equation, v equal to root 2gh in this equation, we are going to get height equal to m square g r square by 2b power 4 L power 4.
Exactly.
By substituting the equation and by squaring it.
So basically, this was hence we derived the formula for the height given in the question. The question seems to be a confusing one, and as in, because nothing directly has been given to us, so but just using again the concept of motional EMF and properly visualizing what is happening in the question, and by the force equations, and keeping in mind all the conditions given in the question, we could find the solution of it. And so thus height came to be m square g r square by 2 b to the power 4 L to the power 4. So this was question number 11. So, coming to question number 12, it says, refer to the diagram given below, calculate the mutual inductance link between the two discs given to us. So, basically, we see that BD is greater than R here, and R is greater than BD here. These are the assumptions given to us in the question. We could assume them to be R being the bigger radius, and B being the smaller radius, and BD being the resistance between both of them. So, here we have to find the mutual inductance. Let's see how to proceed.
I taught you the concept of mutual inductance earlier, right? And because of the current, to calculate the mutual inductance and the sense of current I in this bigger ring. So because of this, we will calculate the mutual, flux developed in this smaller ring. So these assumptions will help us to calculate the flux properly and accurately.
That's
so
right.
Let me think that the ring as x and this ring as y, and the flux in the ring y would be m into ix, and where m is the mutual inductance, we are going to calculate it.
Exactly.
So let me think, because of this y, because of this ring, let me think this as a dipole, and because of this dipole, we can calculate the B at this point.
Exactly.
B at this point, because of this ring, would be B at y. Because of the ring, would be mu naught by 2 pi Ix into 2 pi r square by r square plus d square or 3d by 2. We have done it before. This is nothing but the area of this disk.
That's right, pi r square.
We have taken assumption that d is greater than r. So this would turn to mu naught Ix
By 2
square by 2
dd cube.
2d cube.
That's right. Because exactly, the approximation technique thing, it just reduces our time, and moreover the options in the competitive exams are not really that nearer to each other. So in fact, when we are to find the numerical value also, even then we can use these approximations as the same our time.
So at a distance d, it is also given that d is greater than r, no, and because of this ring, the field at this distance would be uniform, almost uniform, and the field would be almost parallel to the smaller ring.
Right.
So the flux in the for smaller ring would be b by into area of the smaller ring, pi into small r square.
Exactly.
So that's nothing but mu naught Ix r square by 2 d cube into pi into small r square. That's nothing but comparing the above equation and this equation, we will get M as this term. This is the constant.
Exactly.
So the mutual inductances of the two circuits will be R square by 2 d cubic.
That's right. So basically, this was a question on mutual inductance, a concept commonly asked in competitive exam nowadays. So this was question number 12. Coming to question number 13, we see that we are given an AC circuit for which the voltage is something like 100 sine of 100t and the current is 100 sine of 100t plus pi by 3. Now we have to find the power dissipated in the circuit. Basically हमें AC सर्किट दिया है, V0 की वैल्यू हमें 100 पता है, I0 की वैल्यू भी हमें 100 पता है, ओमेगा भी वी कैन सी कि उसकी वैल्यू भी 100 है एंड द फेज डिफरेंस बीइंग पाई बाय 3. तो हम लोगों को पावर डिसिपेटेड निकालनी है. लेट्स सी हाउ टू डू दिस क्वेश्चन.
The power dissipated, there is a direct formula for this. The power dissipated is equal to V RMS into I RMS into cos phi. We know all this. Cos phi is equal to R by Z. And we are given that phi is nothing but the phase difference between V and I. So the phase difference given is phi is minus pi by 3.
That's right.
By seeing the equation. So V RMS is nothing but V match by root 2. We all know this, right?
Exactly. It's just a formula.
It's actually the RMS is nothing but the normal current given for us. IRMS is also 100 by root 2. By directly solving this equation, we can get the answer. It will become 100 by root 2 whole square into cos minus pi by 3. That is 10 power 4 by 4. Basically, all students make a mistake in finding VRMS. They take directly as 100. They won't divide by root 2. Otherwise, this is a very simple question.
Exactly. The catch here was that the V should be taken carefully, the VRMS thing, that dividing by root 2 should not be forgotten, because 100% in some other option they would have given where root 2 would not be involved. So it would be very tempting to do this question wrong. Although it's a very easy question, just the formula application, but we need to be careful in such questions, and these numericals are also commonly asked and direct formula application it is. So this was question number 13 for the chapter. Coming to the last question for the chapter question number 14, it says, refer to the diagram below and given that the steady state is attained and I2 is equal to 3 ampere, we have to find the potential difference along the 4 ohm resistor. Let's see how to proceed in the question.
See here, the current is divided, right, in the two branches.
Exactly.
Total current, let me think the total current is I, and then in the branch 1 be I1 and branch 2 be I2, and I will be I1 plus I2, right?
Right.
And again, when the steady state is attained, the currents will be constant. The current will not be varying. So di by dt will be 0. So here, if you see this inductor, the current voltage across the inductor would be 0 because di by dt is 0.
Exactly.
So because the voltage across this inductor is 0, even the voltage across this 5 ohm resistor would be 0.
True.
So only if the current I1 passes through this, the entire current I1 passes through the inductor and will not pass through the resistor. So the potential difference across AB would be 6I. And let me calculate potential difference across CD. And potential difference across CK, the inductor would be 0 because di by dt is 0.
That's right.
So VCD will be 0 plus 1 into I2 plus 3 into I2, right? So
right.
6 it is 4I2. We know that 6I1 is equal to 4I2 because potential difference across AB is equal to potential across CD.
That's right.
So on solving this we get 3I1 equal to 2I2.
True.
And again it is given that I2 is equal to 3 amperes.
Right.
So I2 equal to 3 amperes means I1 equal to 2 amperes.
Right.
So the total current would be I, which will be equal to 5 amperes.
That's right.
So the potential difference across this 4 ohm resistor would be I into 4 ohm. That is nothing but 5 into 4, 20 watts.
Volt. That's right. Basically, this was an easy numerical, and it just talked about it is, as you can see, it is a normal circuit analysis just including inductor. Now instead of this inductor, there could also have been capacitor. So basically in both these questions, or they could have been both of them, we just use the basic properties of both, the how they behave in the circuit, and just apply those properties to the circuit. And it seems to be a difficult question when we just combine inductor and capacitor and such more things to the question, but it is actually easy to solve if you just apply the basic rules of circuit solving. So this was the last question for the chapter electromagnetism. So basically more and more practice in this line and will give you an idea of a greater visualization, and you will be able to do questions in a better way. So this was for the chapter electromagnetic induction. This was the last question. Thank you.